Okay, now we want to start looking at specific types of discrete probability distributions. The uniform is interesting, it can be useful sometimes, but if you think about it, most outcomes are not equally likely. So it's very limited in as to what it can be used for. Okay. So the first thing we want to try to get down are some basic terms when we're talking about a general discrete probability distribution. We have this thing called the probability mass function, where the probability that capital X is equal to X is just P of X. Okay. Notice this notation. This is kind of important. It says the probability that the random variable takes on this value. Okay. So when we're talking about values of a random variable, we'll use lowercase. When we're talking about the random variable itself, we'll use uppercase generally. And we also want to talk about the support of a random variable. And this is just the points in the sample space where the PMF is not zero. PMF is what we call probability mass function. Okay? So it's where we have probability. A very important function is a cumulative density function. This is the probability that capital X is less than or equal to X. Okay? And how do we compute the probability of an event? Well, we simply add up the probability that each of the elements in A occurs. So we take a sum over all the elements in A. Okay, that are also in the support of X, I should add. So with this, we can do a couple of important things. The first is we can look at the expected value of some function of a random variable. So we're going to say that g of capital X has an expectation value that's basically the weighted sum of the values of the function times the probability that this random variable value will occur. Okay? And this is taken over all the points in the sample space. A couple of important things about expected values. First of all, the expectation operator is a linear operator, meaning that it distributes across sums and scalars factor out. Okay. Another important thing is that if X and Y are independent random variables, the expected value of their product is the product of their expected values. So these are two important properties of expectation operators that we use a great deal. Now, two expected values that we use a great deal are, first of all, the mean of a random variable. So this is just when g of X is equal to capital X. And so the expected value of X, which is the mean, is just the values of X weighted by the probability that those values of X will occur. And we sometimes call the mean the first moment. Okay, it's like the center of mass if you go back to your physics, okay, where the PMF is the relative density in a sense. Okay. Properties of the mean that are really important. You can prove these. You can prove that the expectation value for the mean distributes across. Okay, this follows right from the fact that the expectation operator distributes. And if we take a random variable and multiply it by a constant, the mean of this new random variable is the constant times the mean of the old random variable. And again, these are things that you can prove right from those properties we discussed a second ago. The second sort of expectation value that we are interested in computing is the variance. So this is basically the deviations of the random variable from the mean, the squared deviations. Okay. And when we take their expected value, that's the variance. Now you can prove that you can rewrite this so that it now becomes the expected value of X squared minus the square of the expected value of X. You can prove it from here, you can get to here. And this is what we often use. Okay, there are some important properties of the variance. The first is a scaling property that says if you form a new random variable, which is a constant times the old random variable, its variance is going to be the square of that constant times the variance of the old random variable. And you can prove that. That follows directly from this formula. There's an additivity property that's very important. It says that if you add a constant to a random variable, the variance does not change. Now that should be when you think about it, because the variance is the square of the standard deviation, and the standard deviation is a measure of the width of the distribution. So with this new random variable, what are you doing? You're just translating the whole distribution, so it shouldn't affect the width. Although you can prove it again from this definition right here. Something that's very useful is the fact that if x and y are independent, then the variance of their sum is the sum of their variance. Generally is not true, okay, but in this case it is. Okay, now we want to look at some specific distributions. So the first is the Bernoulli, which is a single experiment with two outcomes. We're going to label them 1 and 0, just like before. Success is usually denoted by x equal to 1, failure is x equal to 0. And we have the probability of success being p, and of course probability of failure has to be 1 minus p, which we sometimes call q. And the PMF for this is given as follows. Okay, and you can show that if you use this PMF and you compute the expected value, you should get p. Okay, and I'll leave that as an exercise for you to show. You can also show that the variance, when you substitute this PMF into the formula for the variance, ends up being p times 1 minus p. And again, I'll leave that as an exercise for you to show. Now, one of the distributions that comes from the Bernoulli is the binomial. So here we're envisioning a situation where we have n Bernoulli trials, and they're independent of one another. Like you flip a coin, right? What happens on the first toss has no effect on what happens on the second toss. That's independent, right? And the probability of success is the same for every trial. Then we say that the number of successes, which we're going to call capital X, has a binomial distribution, and we denote that as follows. And this is the PMF for the binomial distribution. Notice this binomial coefficient here. Okay. And we can easily derive this, because the probability of any specific string of x successes and n minus x failures is given by this. Okay, if these things are independent. And how many strings can we have? Well, we can have n factorial ways of arranging n things, but notice that there's a redundancy. There's x factorial successes, so we have to divide by x factorial. There's also n minus x failures, so we have to divide by n minus x factorial, and that's where we get this factor. And of course, we multiply these and we get the PMF. Now, there's a very important property of the binomial distribution that you should know. And as you think about it, a binomial random variable is really just the sum of independent Bernoulli random variables, right? So it turns out that I can rewrite the number of successes as the sum of what we call these indicator random variables. Okay, where they're 1 if I have a success on the ith trial, and 0 if I have if I don't have a success on the ith trial. And you notice that these indicator random variables are actually Bernoulli random variables. The probability that you have a success is p, and it takes on a value of 1 or 0. These are really Bernoulli random variables. And we use the word IID. IID means independent, because the Bernoullis are independent, and identically distributed, right? And this actually makes finding the mean and the variance of a binomial distribution very easy, because you notice, and I'm going to let you prove this, you should prove this, that, you know, but we've already done this, right? That if it's a Bernoulli random variable, the expected value, the mean is p, the variance is p times quantity 1 minus p. So it follows automatically that the expected value of x is just equal to the sum of the expected values of the Bernoulli random variables. And these are all the same, they're all p. So I sum up p n times and I get np. Okay? And this result makes sense. If I flip a fair coin 100 times, how many times should I see heads? Well, n's 100. Fair coin means p is a half. I expect to see heads 50 times, right? Notice the same thing is true for the variance. The variance of x is the variance of the sum of these Bernoulli random variables, and they're independent. That's important. So therefore, the variance of the sum is the sum of the variances, and we know each of these variances, so we just have n of them. Okay. Otherwise, if you don't use this result, this is actually very hard to do on your own. Okay, the geometric distribution is the next one we want to look at. And so here we have the same sort of thing. We have a sequence of independent Bernoulli trials, and the probability of success is the same every trial. But what we're interested in is we're trying to figure out the trial on which the first success occurs. And that random variable has a geometric distribution. And we write it as x distributed as geometric p. Geometric distribution with parameter p. And this is the PMF. Okay, so the success can occur in the first, second, third, and ... Okay, actually there's no let me change one thing real quick. Be a little careful. This is actually any integer. Okay. And again, it's actually easy to derive this PMF because the probability that we have all failures on trials 1 to x minus 1 is just 1 minus p to the x minus 1. And then we have a success on the nth x trial, that's just p. And so we get this result. Okay. Now if we want to compute the mean and the variance, they aren't too difficult. I'll show you a little trick that's very handy. We start off trying to compute the expected value using the formula, just like we've been using. And we notice something. We notice that this x times 1 minus p quantity to the x minus 1 is really the derivative of the quantity 1 minus p to the x power with respect to p. And so if I use that fact, okay, I can figure out that the expected value is 1 over p. And you can go through this derivation. It's not hard once you know this fact, though. Okay, all I have to do is multiply by p, right? I have my result. And the variance is the same way, except sometimes we want the variance. We're very tricky. What we do is we compute the expected value of this quantity. And notice this gives us the expected value of x squared, the expected value minus the expected value of x, and from that we can get the variance. Because the reason why I want this is you notice that this is basically can be rewritten now as the derivative of this quantity raised to the x power. And if I use that and go through all the mathematics, I end up finding this. And so if I add the expected value of x, which is just 1 over p, I get the expected value of x squared. I subtract from it the square of the expected value of x, and when I do, I get q over p, and that's the variance. Okay? So geometric distribution is useful when we're looking at the first trial on which a success occurs. Poissons are very useful also because they model a lot of things in real life, and so we have some assumptions we make. We have this notion that there is some interval we're interested in. It can be length, it can be time, sometimes it's area, okay? And we have events that are occurring independently, and we know the rate at which they occur per unit interval, okay? And if this is true, then x is said to have a Poisson distribution with parameter lambda, where this is our rate per unit, interval. And the PMF is given by this. Notice that x can be 0, 1, 2, anything, right? So this is a countable, infinitely countable sample space. And you can show, I'm going to let you prove that the mean is lambda and the variance is lambda. I'm going to leave that as an exercise for you. There's a very important property of Poisson distribution that's worth trying to understand. It's a scaling property. And I want to give you an example of how this is used. So let's suppose we're given a problem where vehicles pass through a junction on a busy road and there's an average of 300 per hour that pass through. Now, I want to find the probability that no vehicles pass through in a given minute. So what I'm going to do is I'm going to scale this lambda. You can always scale the rate. It makes sense, right? If there's 5 things that happen in 10 seconds, then on average, there's going to be 1 thing that happens every 2 seconds, okay? So it makes sense this rate scales. So now this is 5 passing through each minute. This is my new lambda. And of course, the probability that none occur is when I evaluate this at 0, and I get e to the -5th. Okay. What is the expected value passing through in 2 minutes? Well, my lambda is just going to be twice this, and so the expected value is equal to lambda, which will be 10. Okay. Now it says find the probability that this expected number actually pass through in any given 2-minute period. Well, the value I'm interested in is 10, so the probability that 10 occurs when lambda is 10 is given by our formula, and you can go ahead and compute that out. Okay, so those are the major discrete distributions. Now we're going to talk a little bit about continuous distributions next.